All right, hey class. On our individual presentations here regarding jet performance, I'm going to be talking about climb, climb rate, climb angle, and best rate, how to find those using the graph. I'm going to be referring to the graphs in the book, specifically the T-38 aircraft, and that's by me. All right, so first off, before we get started talking about this, just some basic assumptions and forces that we kind of want to understand in order to kind of get fully grasp what's going on here. This diagram from the left is from our book, and what's going on here is the aircraft, we're assuming it's at a constant velocity climb, so everything is at equilibrium. So forces, the forces involved here are lift, weight, drag, and thrust. So lift is acting 90 degrees to the flight path. And then you have weight, which acts towards the center of the Earth. That's that W vector you have there. And then you have another weight vector, which is that W cosine of Y. And that's acting perpendicular to the flight path. And then you have that W sine of Y, which is acting parallel to the flight path. All right, so now that we got that sort of this in context here, so the angle of climb is the first thing we're going to want to kind of talk about. So to solve for this, I just used this diagram straight from the books for the T-38 thrust available, thrust required diagram. And as you can see here with it, as your initially you have more thrust is required at a lower airspeed velocity, and then it goes down, down, down with velocity to a certain point there, and that point is actually going to be your LD max, and that thrust required point of 830 pounds you see on the graph. That's your LD max point. And from there, if you remember from last week, it's going to start going back up because the aircraft's going to need more thrust in order to compensate for that extra drag that we're getting as a result. At this point, it'd be mostly as a result of parasite drag. But then it's going to go up, 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 and then you get to the point on that graph where you get thrust available at 100% RPM. So those 2 points are going to be the points we're going to be looking at when we're going to be talking about the best angle of climb. And we'll use this equation here. Sine of y is equal to it's going to be thrust available, so that's your max thrust available, TA at 100% RPM minus thrust required. So if you look at any point on that graph, you can see what thrust is required at a particular airspeed, and then you subtract those, and then you divide it by your weight, and that's going to get you. Then you got to take the inverse sine of that in order to figure out your angle of y, and we'll do that in the next slide here. But that's how you're gonna find just your angle of climb based off of this diagram. All right, so with that, again, puts things a little bit of context on how to just find the angle of climb. We're gonna be using that same diagram here again to find the best angle of climb for this T-38 aircraft. We looked at the diagram. So we're going to be taking that. We're going to be using that TR and that TA at 100% RPM. So our assumptions here is that this aircraft is at max takeoff weight, which is about 12,700 pounds. TR, based off the graph, is 830 pounds, and then TA, it looks like it's around 4,200 pounds to me. So if we put that into our equation there, sine of y is equal to 4,200 minus 830 divided by 12.7, and it gets about 2.65354. Then we got to take the inverse sine of that, and it ends up being about 15.39 degrees is our best angle of climb. And again, that's at that point where the aircraft is at LD max, so it's at that minimum drag spot. And this diagram right here in the middle kind of shows that and the relationship between thrust and the velocity, and the drag as well. All right, so the next thing I want to talk about is the rate of climb. So the difference between rate of climb and angle of climb is one references a time and one is reference to a distance. So the angle of climb is saying, okay, the aircraft can get to a particular altitude over a certain amount of distance, where rate of climb is saying the aircraft can get to an altitude over a period of time. So the best rate of climb is going to be the altitude, the speed, um, or the rate, I guess, that the aircraft can climb to a particular altitude over the shortest period of time. Where the best angle of climb is the angle that the aircraft can fly in order to get to a particular altitude over the shortest amount of distance. And that diagram on the top left kind of illustrates that point pretty well. And then also the one below it, just for practical purposes, also illustrates that. And like if you're doing a short field technique or something like that, and you need to clear some trees at the end, you'll more often than not you'll probably be utilizing the best angle of climb in order to clear the trees, and then you'll accelerate to best rate in order to get to your altitude in the most efficient manner possible. So in order to find this rate of climb in general, we're going to utilize this formula here on the top right. And you can see there at the bottom that 101.3, that's just a conversion factor. So we can get from knots to feet per minute. And you notice that it's really similar to the angle of climb. You're taking that, the thrust available, subtracting it from the thrust required, and dividing it by the weight. So that means that, again, the best rate, if we do go to solve for that, is going to be at that point where LD max is at. It's going to be that velocity. And that's going to give us that best rate. And then you can also see this relationship right here on the right lower hand corner, the rate of climb and velocity. So it goes up. The rate of climb goes up with velocity to that certain point, and then the aircraft is no longer as efficient because more drag is occurring. Again, at those higher airspeeds, it's going to be mostly parasite drag, and then your feet per minute is going to start dropping off. So we'll talk a little bit more about this and give a specific example in the next slide. All right, so I want to talk a little bit more about rate of climb. So again, using this graph to the left here, I'm going to talk about how to find the best rate of climb. And you can do this at any point on the graph, but for best rate, again, we want to look at that LD max point because that's the point where we have the least amount of drag, and so the least amount of thrust required, and that's going to give us that greatest distance between thrust available and thrust required, and therefore give us the best rate of climb. So again, assuming maximum takeoff weight 12.7, and then thrust required 830, thrust available at 100% RPMs 4,200 pounds, and then based off this graph, it looks like we're about at 250 knots or so. So the rate of climb, again, that conversion factor, that 103.3 times the 250, and then those numbers there, and then we end up getting about 6,852.77 feet per minute. So anything past that, we're not going to be getting that same rate, and it's going to take us a little bit longer in order to get to altitude.